Assalamu alaikum. Today we are going to continue our chapter number 5, which is about present worth analysis. So we saw in the previous video when the useful life is the same as the analysis period. So we said that this is the easiest case, and we have useful life is the same as analysis period. Now we are going to see the second case when useful life is different from the analysis period. So in present worth analysis, there always must be an undefined analysis period. It follows then that each alternative must be considered for the entire period. In previous examples, the useful life of each alternative was equal to the analysis period. This is what we saw in the previous section. Often we can arrange it this way, but in many situations the alternative will have useful life different from the analysis period. So let's see an example. Diesel manufacturing is considering the two alternative production machines graphically depicted in figure. Specific data are as follows. So we have two different machines, two alternative for two different machines. The initial cost for the alternative one is $50,000. The initial cost for alternative 2 is $75,000. Estimated salvage value at the end of useful life is $10,000 for the alternative 1 and $12,000 for alternative 2. And useful life for equipment in years. So the useful life for alternative 1 is 7, and the useful life for alternative 2 is 13. So they have different useful life, and the manufacturer used an interest rate of 8% and wants to use the present worth method to compare this alternative of an analysis period of 10 years. So as you see here, the analysis period is 10 years, and the useful life for the alternative 1 is 7, and for the second alternative is 13. So there is difference between the analysis period and the useful life. In this case, we are going to see how to solve this problem. Estimate market value after 10 years. We have alternative 1, it's the machine, or the alternative 1, it has estimated market value 20,000, and for the second alternative 15,000. This is after 10 years. Okay, so if we would like to draw the cash flow of this situation, we have initial cost, of course, and after a 7-year life for the alternative 1, we have a replacement cost. So salvage value is 20,000, and you have to buy another machine to continue the 3 years. Okay, so 3 years here, and this is the salvage value, and this is the value in the market after 10 years. Of course, it's the market value after 3 years of the machine number 1, or the alternative number 1. So in this case, we have to sell the machine and buy another one to cover 10 years. Okay, and for the second alternative, the initial cost is here, and since the useful life is 13, so we are going to cover only 10 years, and we have only the market value after 10 years here. Okay, so in the first alternative, we pay the machine at the beginning of the cash flow. After 7 years, this is the end of the useful life, so we have to sell the machine and we buy another one to cover the remaining 3 years. In this case, the useful life is bigger than the analysis period, so in this case we just cover 10 years using the second alternative, and we are going to calculate the present worth for both alternative, and we would like to make a decision regarding these two alternatives. So the present worth alternative 1 is minus 50,000. This is the initial cost of the machine. when we buy the machine at the beginning of the cash flow, plus 10,000, which the salvage value, minus 50,000, which is the cost of the replacement of the machine. Okay, this is considered as a future value. So looking for P given F 8% 7 years. So this is the salvage value, and this is the cost of a second machine to cover the remaining 3 years. Okay, plus 20,000, which is the estimated value at 10 years. 20,000, looking for P given F 8% 10 years. So we get the present worth of the first alternative is minus $64.76. Now for the second alternative, we have minus 75, which is the initial cost at the beginning of the cash flow, plus 15,000, which is the value after 10 years. 15,000, looking for P given F 8% 10 years. So we get minus 69.442. So as you see here, this one for alternative 1 is less than this one. Okay, so using the present worth, we have to take alternative 1, which has less present worth than alternative 2. So it's better to buy the machine here, after that sell the machine after 7 years, and take another machine, or buy another machine to cover the remaining years. So alternative 1 is best than the alternative 2. So this is how to make analysis when we have useful life different from the analysis period. Okay, so this is about this section. Now the third case is infinite analysis period, and what we call capitalized cost. Some service or condition sometimes must be maintained for an infinite period. The need of road, for example, dams, pipelines, and other components of national, state, or local infrastructure is sometimes considered to be permanent. For example, when we make a road, it's supposed to be the useful life should be very long, so we can consider it as permanent. In this situation, the present worth of cost analysis would have an infinite analysis period, and this particular analysis is called a capitalized cost. Capitalized cost is the present sum of money that would need to be set aside now at some interest rate to yield the funds required to provide the service, or whatever indefinite. That means we have to put aside, يعني نحطه في البنك some of an amount of money, and from the interest we can cover the cost of the infinity. The money set aside for future expenditure must not decline. The interest received on the money set aside can be spent, but not the principal. That means here we have the future value is P, which is the present value, plus IP. This is the interest for n equal to 1. Okay, so this is our equation. For an initial present sum P, there can be an end of period withdrawal of A IP. That means if we put in the bank P, after 1 year I get IP. So I can take IP, I spent IP, and I keep P in the bank. So in the next year I get also IP, and so on. And this withdrawal may continue forever without diminishing the initial sum of P equal for n equal to infinity. So the basic idea is to put a sum of money P, and after every year I take IP, only IP, and I keep P in the bank. So I take IP that I can spend for any project. So capitalized cost is therefore the P in the equation A is IP. So capitalized cost P is A over I. So A is IP. This is the amount that every year I can take it from the bank without and keeping P the initial amount in the bank. So every year I get A, which is equal to IP. So from that I can get the capitalized cost is A over I. I the interest rate. Example, how much should one set aside to pay $50 per year for maintenance on a graph site if interest is assumed to be 4%. For perpetual maintenance, the principal sum must be remain and diminish after making the annual interest. So we are looking for the amount of money that we put in the bank, and every year I take only the interest, which is $50. So how much I have to put in the bank to get every year 50% as interest, amount of interest. So here capitalized cost P is A over I. So A is $50. I would like to get every year $50 and I 4%. So I have to put in the bank 1,250, and the interest will be every year $50 when I take from at the end of the every year $50. So the amount will be the same every year. It will be 1,250, and I get 50% every year as $50 every year as interest. Now another example, city plans a pipeline to transport water from a distance watershed area to the city. The pipeline will cost 8 million and will have an expected life of 70 years. So the pipeline has a useful life 70 years. The city anticipates it will need to keep the water line in service indefinitely. Compute the capitalized cost assuming set percent interest. So here we have, since the expected life is 70 years, we have to keep indefinitely the service. We have every 70 years we have to pay 8 million to construct the pipelines. So we would like to get to put an amount of money in the beginning of the cash flow, and every year we take value A during 70 years. When we get when we finish 70 years, we should get 8 million to construct again the pipelines. So here we have capitalized cost P. We have 8 million paid in the beginning of the cash flow. After 70 years I have to pay 8 million to construct again the pipelines. After 140 I have to pay 8 million to construct the pipeline, and so on until infinity. So every 70 years I have to get 80 million. So A is F, which is the future value, 8 million, multiplied by the factor looking for A given F, I% n period. So it will be 8 million, which is the future value that the amount that I'm going to use to pay the pipeline for 70 years, every 70 years. A looking for A given A F 70%, 70. So we get 4,960. So every year I have to get from the interest 4,960 during 70 years. At the end of 70 years I get exactly 8 million. So the 8 million disbursement at the end of 70 years may be resolved into equivalent amount A. So during 70 years, if I put $4,960, I can get after 70 years 8 million. Each 70 years period is identical to this one, and the infinite series is shown in the figure. So we get 8 million in the beginning, we have to pay 8 million. After that we get a uniform series of the value for 4,960. So I get at the end of 70 years 8 million. So the capitalized cost P is 8 million plus A over I, which is 8 million. $70,857. So this is the capitalized cost here. So it's 8 million, the first amount, and the rest will be distributed as a uniform series. So alternative solution, or alternative solution 1, instead of solving for an equivalent end of period and payment based on a future 8 million disposals, we could find A given a present value 8 million disbursement. So A is P, this P, which is 8 million. Looking for A given P, I percent N, N years. So 8 million, which is the first amount. A, looking for A given P, 7%, 70 years. So I get $565,000. So on this basis, the infinite series is shown in figure. So we have 8 million, we get 5,065,000 every year, and at the end we get 8 million. So the capitalized cost is A over I. So it's 8 million 71,000. So this is when I put this amount at the beginning of the cash flow, I get interest 565,000. I take a withdrawal every year 565,000, and at the end I get 8 million, which is the cost of the next pipeline. Another way to solve the problem is to assume the interest is 70 years, compute an equivalent interest rate for the 70 years period, then the capitalized cost may be computed by using equation. So from M or N equal to 70 year, the interest rate it will be 1 plus A to the power of M minus 1. So I of 70 years, the interest rate of 70 years is 1 plus 0.07, which is the interest rate per year, to the power of 70 minus 1. So we get here 112.989. So this is the interest rate for 70 years, for the total 70 years. So capitalized cost is 8 million plus 8 million divided by the interest year for 70 years. So we get 8,071,000. $710,000. So in here is missing 0. Okay. So this is an alternative to deal with an infinite period. Now let's make the last example. An investor paid $8,000 to the consulting firm to analyze what he might do with a small parcel of land on the edge of town that can be bought for $30,000. In their report, the consultant suggests 4 alternatives. So the consultant suggests 4 alternatives. The alternative A is do nothing. We do nothing. We don't. So we get 0 as a terminal value. Vegetable market. We make a vegetable market in the piece of land. So the total investment is 50,000. The uniform net annual benefit is 5,100, and terminal value at the end of 20 years is 30,000. This is the second alternative. C, we make a gas station in this land. So the cost is 95,000. The uniform net annual benefit is 10,500, and the terminal value at the end of the 20 years is 30,000. And the alternative D, small motor. The the cost is 350, the annual benefit 36,000.